So for this video, let's talk about proof by induction, at least at the basic level. So why do we need proof by induction, and why is it such an important method in mathematics? Well, there are many formulas in mathematics and science that we cannot derive, but we can just motivate them into existence, or some of them are just got by observing patterns in numbers. One good example of such formulas is Gauss's formula for the summation of n counting numbers, which is n into the n plus 1 divided by 2. So you cannot derive this formula, but it's just something you get by observing a pattern in adding, counting numbers. So such formula can be proved using the method of induction, which is one of the methods of proving formulas in mathematics. So let's begin with this as a first example and see how the method works. Now, the first thing we need to do is to test whether the formula works, and we do that by putting in a few numbers here. So let's say for n equals 1, if you just look for just the sum of one number, you're looking at only one number here. If you put n on the right hand side, you'll have, as 1, in this case n as 1, so you have 1 into 1 plus 1 divided by 2, which is also a 1. So the formula holds for n equals 1. Okay, so let's try out for, that's a 1. So let's try it out for n equals 2. Let's see if that works. So n equals 2 means we are adding the first two numbers, this and this. So obviously that's going to be 1 plus 2, which is 3. Let's do it here. Put n as 2. So that's going to be 2 into 2 plus 1 divided by 2. Obviously this cancels and we have a 3. So the formula works for the first few numbers. And now the question is, will this formula work for all numbers, for up to n numbers? Let's go ahead and prove that. So we've just seen that the formula holds for n equals 1, n equals 2, probably n equals 3, and so on. So let's assume, so I'm going to assume the formula holds. So I'm going to assume that this formula holds for some arbitrary value of n. Let me call that value k. Alright, so just create this here. So let's suppose the formula holds for n equals to k. That means if I have 1, 1 plus 2 plus 3 plus, any number of times here, plus k, it should give me k into k plus 1, right? K into k plus 1 divided by 2, okay? And now, the big question is, if it holds for any number n is equal to k, does it hold for n equals to k plus 1? So this is the big question. Does it hold for n? Okay, does it hold for n equals k plus 1? In other words, if it holds up to n equals to k, what if I add another term here, which is k plus 1? Will that still hold? Will the formula still be valid? Now let's go ahead and see whether it will. Now, since we want to add another term, k plus 1, I'm just going to add k plus 1 to the left-hand side and k plus 1 to the right-hand side and see how that works. So we have 1 plus 2 plus 3 plus any number of terms here plus k, and then k plus 1. We'll do the same on the right-hand side. So we have k into k plus 1 divided by 2 plus k plus 1. Okay, now this is of course an obvious thing and it doesn't tell us anything about the formula. So we want to concentrate on the right hand side and see if this formula can be equated to what we started with. So just going to create more space here. Let's try to massage this formula a little further and see. So let's factorize out k plus 1 and see. So we have k over 2 plus, okay, so what do we have? So that's factorized out, then I just have a 1 here. Alright, let me also factorize out this a half. So I have a half into k plus 1. Inside the brackets here, what's that? So that's going to be k plus 2. Now let's see if this is comparable to what we started with. I'll just take you back to the start. We said this formula 1 plus 2 plus 3 up to n equals n into n plus 1 divided by 2. Now n has been replaced with k plus 1. Let's see if that is comparable. So let's get another color here. So our formula is n into n plus 1 divided by 2. Let's see if this looks anything like it. By the way, just write this as a half just to make this look nicer. So that's a half into k plus 1 into k plus 1 plus 1. You'll see shortly why I'm writing it like this. Alright, now let's check. See, we have n and we have k plus 1 here. Remember, n equals k plus 1 at this step. So n, k plus 1, n here is k plus 1 plus 1 plus 1. So the formula indeed holds for all values of n, and there we have it. We've proved that this formula actually works. Okay, so let's go ahead and prove it for another common formula, which is the summation of square numbers. So let's have 1 squared plus 2 squared plus 3 squared all the way up to n squared, and this is n over 6 into n plus 1 into 2n plus 1. Okay, so let's begin by testing whether the formula works for the first few values of n. So for n equals 1, of course we have 1 squared, which is 1. On this side we have 1 over 6 into 1 plus 1, that's a 2. Well, 2 plus 1, that's 3. Obviously this is 1. Okay, for n equals 2, let's see what we have here. We have this plus this, the first two terms. That's 1 plus 4, which is 5. On the right hand side we have, that's n equals 2, so 2 over 6 into 2 plus 1, that's 3. 2 times 2 plus 1, that's a 5. Obviously 2 times, okay, just write this well. So 2 times 3 is 6, divided by 6, that's 1 times 5, so this is 5. So the formula holds for the first few numbers. Now, we've seen that it holds for the first few numbers. Let's suppose or assume, so we'll suppose that it holds for any arbitrary number. Let's say n equals to k. And by the way, this is what we call the induction step, where we are supposing that this formula is true for some value n equals to k. So that means 1 squared plus 2 squared plus 3 squared all the way up to some number k squared will be k over 6 into k plus 1, 2k plus 1. Alright? Now, if this holds for n equals to k, the big question here is, does it hold for n? So does it hold for n equals k plus 1? Okay, so we've just seen that it holds for n equals to k, and we want to see if it holds for the next term, n equals to k plus 1. Okay, let's do that. So we have 1 squared plus 2 squared plus 3 squared all the way up to k squared plus k plus 1. Don't forget to put the square. Alright, so this, on the right hand side, we have k over 6 into k plus 1 into 2k plus 1 plus, okay, got to add more space here, so plus k plus 1 squared. Hope you see that square over there. So we want to see if it holds for this. We've added another term, k plus 1 squared, on both sides, and this is really the step that proves whether the formula is true or not. So let's go ahead and simplify what we have on the right hand side to see if it matches or is comparable to the expression that we began with. So this is going to be, let's see, let's factorize out k plus 1 here. and see what we have inside the brackets here. So I have k over 6 plus, this is 2k, not plus, that's actually into 2k plus 1 plus k plus 1. Alright, so the second thing I'm going to do here, since the original expression had n over 6, I think it's better to factorize out this 6 at this stage. So I have, let's just write this as k plus 1 over 6. So inside here we have k into 2k plus 1 plus, this is going to be 6 into k plus 1. Alright, just add more space here. So this is k plus 1 over 6 into, so this is 2k squared plus 2, no, that's not 2k, plus 6k, I'll just write 7k here, plus 6. Alright, this is nice. Let's see if this thing right here can be factorized. I'll just do that here. So we have 2k squared plus 7k plus 6 plus 6. So let's see, that's 12. So I'll write this as 2k squared plus 3k plus 4k plus 6, just splitting up the 7 into 3 and 4. So I can factorize out k in the first expression here. So I have 2k plus 3. I can factorize out 2 from here. So I have 2k plus 3. I factorize out 2k plus 3. So I have k plus 2 here. Alright, so we have it there. Let's now write it here. So I have k plus 1 divided by 6 into, I would rather begin by writing this k plus 2, then I have 2k plus 3. Now let's see if this is comparable with what we started with. Don't forget we started with this formula here. 1 squared plus 2 squared all the way to n squared should be equal to n over 6 into n plus 1 into 2n plus 1. So just bring you back here. So there we are, n over 6 into n plus 1 into 2n plus 1. So let's see what we have here. Okay, maybe I just need to clean up this a little, one step further. So I have k plus 1 over 6, then I have k plus 1 plus 1, right? Then I have 2 into k plus 1 plus 1. Alright, so as you can see here we have n. Remember, this is for n equals k plus 1. Don't forget n is k plus 1. So we have n here, we have k plus 1. We have n here, we have k plus 1 plus 1. Then we have 2n, which is this right here. And then we have this 1. So the formula is true by induction. Alright, so thanks for watching this video. I hope this video gives you a nice introduction to the basics of what proof by induction is and how to do some of these beginner proofs. I'll make another video where I talk about this in great detail and solve quite a number of examples to make this concept a little bit clear. So until then, thanks for watching. If you haven't subscribed to the channel, by the way, please do so. Also click the notification bell to get notified every time I upload a video. Thanks for watching. See you again.